Now, we're ready for our first speaker, and he is someone who used to be a professor of autonomous intelligent systems at the University of Freiburg in Germany. From 2019 to 2021, he was VP for Automated Driving and Machine Learning at the Toyota Research Institute, and he's published over 400 papers and received multiple awards. For example, the Leibniz Prize of the German Research Foundation. So please welcome on stage from the University of Technology Nuremberg, Professor for Robotics and Artificial Intelligence, Dr. Wolfram Burgard. Welcome.
Wonderful to be here. Thanks for the kind invitation. I'm looking forward to describe you a little bit of talk a little bit about this journey of robotics and AI, and then hopefully having a discussion at the very end. If you look at what we are aiming, give me 1 second. High tech, low life.
Maybe a bit higher.
No, here we go. So in robotics, we are basically aiming at building robots for solving societal challenges, or at least contributing to these solutions that is making traffic safer. We are interested in or looking into making production more efficient in these global competitions that we are having. We are thinking that we can actually contribute to future healthcare and also feeding the world in a better fashion. This is some of the goals that we are actually aiming for and why we are interested in building robots. When it comes to intelligence, we are considering robots being systems that perceive their environment, reason about what they sensed, and then also try to generate actions to achieving their goals. So it's basically that the physical implementation of that, what we call intelligence. So robots are basically nothing else for us than intelligent machines. And in order to build this, there have been several trends in the past that, from my perspective, breakthrough trends that actually advanced the field of robotics. And this was in the 90s, this probabilistic robotics. This was one of the most significant parts of robotics conferences in the world. Then, a couple of years ago, 15 years ago, we had the deep network revolution that came into the game and basically enabled safer driving for self-driving cars. And then a few years ago, we had this foundation model revolution, which is now on the stage to actually building something radically new, and building robots are actually able to better understand the world than any approaches that we saw before. And I'm going to take you briefly through this journey, and at the end, talk a little bit how to combine them as well. So AI does always come with math, right? So that's why this equation is over here. This is an equation that basically shows you how state estimation is being solved. Right? What you have is you perceive the environment, right? And then you want to, for example, want to know what the state of the environment is. This is called SLAM, right? Building a 3D model of this building here. Or you want to know where your vehicle is in the world, given a map. And this is the math that is behind it. It's not just 2 letters, right? It's actually hard math. Right? And here you see this equation in action. Right? This is a robot that tries to figure out where it is in this environment or in this map that you see on the left-hand side. Right? And this time we started, in the 90s, we started with ultrasounds. This was the time when LiDARs came up, right? And before, actually. And here you can see that robots can actually robustly estimate where they are, even if you don't provide them with any prior information about this apart from the map. And the question is, how accurate can this get? And this is something that we worked on in the past. This is an experiment that we did together with KUKA. They basically took this technology and built their mobility. What is this part? I don't know. The mobility part of the company. It's now being sold to China. Talking about China. And when you want to know how accurate this can actually get, then this is an experiment that we did at this time with a prototype built for transporting 747 fuselages in Seattle for Boeing. And this, you can see here that with this technology, you can get to an accuracy of 2 millimeters approximately when it comes to estimating where the vehicle is. And this was a key enabler for these transportation vehicles, logistics applications, and also self-driving cars. So Google were the first ones in 2005 to pick this up and start the work on self-driving cars. because this technology basically allows the vehicle to exactly know where it is on the road. If you want to build a self-driving car, there are 3 things to do. Like stay on the road, right? This here. Right? Second is don't get hit, and third is don't hit anything. When you can accomplish this, then you get really, really far. But this is actually the basic technology and something that is in most of self-driving cars, driver assistance systems, and this equation that you saw before runs even in your cell phone. And so this is a typical software stack of a self-driving car. There you have several components, like you take the sensors, you get the sensor data, and then you do mapping and localization, building a map, figuring out where the vehicle is, right? And then you predict what is going to happen in the world. Then you do planning, like where can I go given my predictions, and then you send this plan to the controller who estimates or to generates the commands that are actually sent to the actuators. And then the question is, like, how can we support such a stack? And the probabilistic robotics one is particularly good at these 2 components that you see here with the thumbs up. That it's my estimate, but it's basically what you see in most of the, when you look at publications and also how this is being implemented and where you find these components of these tools in these components. And this is where we are particularly strong at. Right, and you can also use this for building maps. Just to give you an idea, this is a startup of mine in Freiburg, and we are using this technology for building highly accurate maps of real estate buildings. And this is an indoor-outdoor model of the Leaning Tower in Pisa. It's one of the most accurate models of this building that is available right now. And this is what you can use, for example, for navigation then, and also for real estate. It's obvious, but things might go wrong. If you think about like weather changes, like if you look at what cars basically use, and these are road markings or poles of lamps or traffic lights, but when there's like certain weather conditions, then actually you don't see any of these features anymore, at least the lane markings, right? Which might then lead to the fact that the car actually loses track of its position and ends up on the sidewalk or wherever, right? And this is basically this fact that we are using these maps, which are extremely expensive to generate, is a barrier to the level 5 driving, and that's why we don't see self-driving cars here in Erlangen, right? Because building this map of Erlangen is super complicated and super expensive. And that was kind of like taken over a little bit by this deep learning approach, where we actually could use deep networks for better understanding the measurements. This is basically one example of that, what deep learning contributes. You take an image and label every pixel according to the class that you are seeing there. So basically here you see blue is cars, like violet is road, pink is sidewalk, green is vegetation, and then red is pedestrians and so on. Right? And deep networks are extremely strong in that. The problem is that they only estimate that what we call the maximum likelihood. You get this image, but for post-estimation, you need these probabilities, right? And they are particularly strong in these boxes. And when you look back at that, what I showed before, the probabilistic one, and you see, there might be a chance to combine those two to actually get even better cars. And this is what we worked on in the past, right? In this equation, what you see is probabilities, and these networks don't necessarily provide you with probabilities. And this is where research was needed in order to actually make that happen. And here's one example of how this works. Right, so this is basically segmentation, as we call this, that additionally also produces uncertainties. Right? So you want to know where the vehicle is uncertain about its estimates. And this is something that you can see not only for stuff, but also for instances, which is in the middle and on the right-hand side, the combination of the two. And once you do this, you can actually, and this is a video showing this brighter means higher uncertainty, and you basically see that at the boundaries of these objects, there's a high uncertainty, which is exactly what you would also encounter when you were asked to label these images. And you can then also use this for basically tracking a vehicle with the exact same approach that we saw before. We are combining this deep learning approach with the probabilistic one in a proper fashion. This was quite a challenge, but we are there right now, and this basically enables us to make proper probabilistic reasoning even under the usage of deep networks. But then there was more, right? Recently, there were these foundation models coming up, and when I first saw them, I was actually blown away. So my experiment was like, I'm a robot, I'm standing in front of a doll, my user asked me to pick this up, like where should I grasp it? And then ChatGPT gave me the answer. It always comes with bullet points. So first, like use the arms, the torso, or the legs. Right? Basically, it means don't grasp it at the head. Yes. And then we started looking into this and worked on this a little bit more. This is basically that's what I call a new revolution. That's really towards deeper understanding of the world, and we'll see this in these in a few examples that I'll show. Like this image is here, like it's kind of like a robot ringing an alert bell, because even roboticists are sometimes a little bit tired and slow. They don't drink Coke and coffee every morning, right? And we actually need to realize that we are at an inflection point right now. This technology will be a key enabler for the future robotic systems, in particular when it comes to ease of programming and also flexibility and better understanding of the world. A few examples in a few seconds. Right? There are two approaches right now, using foundation models and then building foundation models for robots. And I'll talk about the first one here. Let me go back. This video should auto-run. Come on, one more, forward. This is an experiment or paper that we worked on a few years ago. We basically enabled the robot to navigate an environment based on language commands. So you see these instructions in the bottom, right? And what we have here is kind of like a 3D voxel grid in the background. And in each voxel, there's what we call an embedding, basically the representation of these objects in the deep network or generated by the foundation model. Right? And once you have this, you can, in a zero-shot fashion, as we call this, right, without any training, tell the robot to basically go to the keyboard, right, or move to the right of the chair. And if you look at scientific publications, right, in the computer vision domain, there are hundreds and thousands papers about detecting chairs in images. Right? And here, it comes out of the box, zero shot. Right? You can even say, like, go to the plant, or go to the keyboard. That's something that you saw before. And in former days, I used to say that it was kind of like every of these objects was a PhD life. You know, you instructed a PhD student, solve this problem of detecting plants. Right? And then you had 5 years, a few papers. But nowadays, you can get this basically for free out of these systems. Yeah, you can also use this for manipulation tasks. Right? So this is basically, as you know, these these foundation models are extremely good at programming. And what we do here is we are basically teaching a robot certain actions. We are telling it what it can do in the environment. And you see this here in this example on the bottom left. This is Oyer, one of my former PhD students, basically teaching a robot to perform elementary actions like picking up a cube, putting it into a drawer, opening the drawer, closing the drawer. And these actions are then annotated with language, and this enables us then to tell ChatGPT, here, this is what I can do. Like, this is a scene. Tell me how I can solve this problem. Right? So this is here the background knowledge that we add. This is me telling the robot to clean up the desk, what I typically do with my students. Right? And then the language model generates a program out of it, which is then in turn used to basically execute the actions. And here you can see this, right, tidy up and turn on the green light, and the robot executes this action sequence generated by ChatGPT then, and just based on demonstrations. Right? So the idea behind all of this is programmers are extremely expensive, and if you want to bring robots into the real world, and in particular for SMEs, right, they don't have the money to pay these super expensive technicians or robot engineers. And the idea behind all of this is that this technology is an enabler for efficient and flexible programming of robots doing tasks that have not been foreseen at the time it was basically built. Here's the grasping example. Right? So it's basically we are asking a foundation model, like where should I grasp the object? And here you can see on the left-hand side is always a state-of-the-art geometric planner. So you give it the geometric model of that object, and it finds these flowers like super great for grasping, right? Because they are huge. And but actually, it doesn't have any understanding of the semantics. On the right-hand side is the language model grasping. Right? So also the cake looks pretty good for picking up. Right? And you can go even further, right? You can ask it about more complex objects, like when it sees a cup with a broken handle, right, then it needs to grasp the body, right? And when it's dirty, then it even grasps it, doesn't grasp it at all. Right? So here's one of the coolest stuff that we did recently. You might ask this question, but how does this run on edge devices? Right? Because we all know foundation models are on super huge computers somewhere in the cloud, and how can we do this on edge devices? And the way we did what we did here is basically we trained a small model based on the policy generated by the foundation model and run that on the edge device, which is a vacuum cleaner. It's basically training the vacuum cleaner to avoid things that it shouldn't suck up. So there is also the most famous example is that picture on the left. So when these vacuum cleaners, I'll be done in a second, these vacuum cleaners basically have brushes, right? And if they brush this up, then they paint your entire apartment with this, right? Which basically makes you like renovating the entire apartment once this happens. And this, you can buy a robot that can do this. It costs several $100 more, and the engineers who generated this have actually been trained or have trained a deep network and classified these. It's plastic, it's not real. These plastic things on to execute this on a real robot. And here taking the policy from the foundation model, training a YOLO V8 from this, and this again is zero shot what you see here, right? So it's not a real vacuum cleaner, that's why it leaves the dirt on the ground, right? And it's also better for making experiments, but you see that it avoids like all kinds of objects that might be harmful for a vacuum cleaner. Out of the box, for free. And you can basically continue with this, and we have many more examples. You can do basically zero-shot action execution of policies in the real world. But the key challenge is actually building a real foundation model for robotics. I show this only to tell you that this is not going to be easy. So this is a paper, the very first one, that were 150 researchers building this all over the world. So it cannot be done in a single lab, and we need to have a huge worldwide effort to build such a foundation model, and we need to carefully think about how this can actually be done. Right? And I'll skip this and show you some aspects like what you can then do, for example. So here's an example where you can actually abstract from environments to actually execute actions. We all know that cameras are super sensitive to illumination and also lighting changes, position changes, and so on and so forth. And this is what we abstract from here. You can basically, my student she, it's a she. That's why the robot has such a beautiful color. Right? So you can basically see that this during training, like you have a completely different robot than you actually see than you have during execution, and this is done by this abstraction through this foundation model. I want to stop here at that time. Right? The next big thing, and this is what is actually missing and why we need actually research and our own foundation model, is because if you really want to build an embedded system that acts in the real world, you also need to have the sense of touch. Right now, foundation models can only talk, or I used to say bubble, or they can only generate images or understand images. But there's no such thing that understands also the sense of touch. And in order to actually properly grasp objects and manipulate objects, you need to have this understanding how the world feels. And this is what is missing right now, and this is why we urgently need a foundation model for robotics that includes exactly this. And there's new sensors coming up right now on the horizon, and when you go to China again, like I was in China 2 weeks ago, there's 120 startups in the space of humanoid robots, and equally many in the space of hands, building hands, with the sense of touch, because they realize that this is exactly what is needed to take the next leap in robotics. With this, I'm done. What I want to let you know is like these 3 techniques are like key for building intelligent and truly embodied systems. And that in the end, we actually need to build a foundation model for robotics to take the next step. As you know, our state minister for research, Markus Blume, is working on this gigafactory thing. And Siemens is also being invited. We will have a workshop in 2 weeks here in Franconia, or 3 weeks, right, where we hope that Siemens will also be involved in that, so that we can jointly build a robotics foundation model that takes us all to the next step in robotics and production. Thank you.
Thank you, Wolfram. Great presentation. And by the way, Siemens will get a lot of information at SPS in Frankenhalle during the SPS, and we will bring that know-how and expertise to the workshop, that's for sure. Great presentation. First of all, I would recommend get rid of the pet. If you have a vacuum cleaner at home like this, or an automatic robot, so you don't have to worry about that. And the second thing, when I think of autonomous driving and you look at all those pictures, it looks a bit like driving under influence. So I'm still worried about that we can go for that. And when you mention there is like, it's so expensive to kind of create this autonomous driving surrounding. It's going to be a long time until we reach that level of that we really can go for it.
Yeah. But it is there, right? If you go to San Francisco, Phoenix, Google or Waymo has done this, right? They invested, I do not know how much, but I think like maybe 10 times 100 million per year, 15 years, like, and maybe 300 million per year. That's what they invested into this. It's a huge investment. I don't see that like the return on investment curve being done, but it will come. And in China, it's also there, right? So I was in Beijing like last year, and they have been like maybe 5 times as fast as Waymo developing this. It's going to come, and we need to adapt to this, and we should not stay behind, right? Even with the same with foundation models, we should not let this go again. We let the search engines go. There's no European search engine. With all the dependency that we see right now, and the same is going to happen in autonomous driving and so on.
Mm-hmm. Any questions from the audience? There is one already.
Hi, thank you very much. Very impressive work. So I was wondering, it works well on chairs, bananas, and so on, but in industry, we very often have very similar looking parts. So I would probably need to fine-tune or retrain the network. So how long does it take from your experience, and how much data, or how practical is it at the moment?
There are 2 aspects. First of all, I think everything can be obtained by using enough data, right? And the question is, what is the cost of? I know we scientists, we are also like believing that we have this tool in our pocket that solves every problem in the world, which is not the case. And so one needs to carefully think about as to whether this investment is proper, right? If it actually needs to a return, positive return in the end. That's one of the questions. But the other one, which is more important, is maybe more on your side, is, of course, you might argue, yes, but this is not good enough for the production processes that we are having. But in the end, we need to search for solutions that can incorporate those. And we need to be able to live with the mistakes that these systems do. Like in self-driving, they have done this. They have basically taken, like there's this roadside assistance team that Waymo uses, and whenever the car gets stuck, there's a roadside assistance team getting the car out of it. And the goal would be to actually minimize these failures. Right? So it's a long-term investment. And this is something that we need to think more about, how we can do this. Right? And not just say, oh, it's not perfect, we're not going to use it.
Mm-hmm. Anybody else? In the last row, to the left, Max? Or almost last.
Yeah, fascinating stuff. Thanks for your presentation. I wonder, how do you match the output of the foundation model with the capabilities of a robot? Because I guess the foundation model will be robot agnostic.
Yeah.
So how do you match type of gripper, max reach, max weight with the output of the foundation model?
So there's a lot of work actually on this cross-embodiment learning. And this is also partly that what you saw in this video, where we basically dressed the robot in order to make it look different. So that they can see that the system can even work with a differently looking robot. Right? But you can also have robots with different kinematic chains. And this is something that we are working on, like how to generalize across it. But it is difficult, right? So when you look at humans imitating birds, like we are flapping always like this, which is not right, right? The bird does this, right? Mm-hmm. So also we are not correct in this embodiment. And so, yeah, but these are challenges, and we are just working on this stuff. And the other one is like how we relate this to the capabilities. This was basically one example is that what Oyer did with training the robot, which actions it can do. And then we use this as a programming language to basically program the robot for executing tasks. As to whether these elementary actions are sufficient for all applications, that's open and which one you need. But there's also works where robots are able to tell that they're lacking a capability in order to perform a certain task. So that they can then ask the user, show me that capability, and then based on this capability, the robot can execute the entire task.
Great, thank you. Any more? Then I have one. Thinking of all these use cases and these attempts and research you've done in your laboratory, how much damage was done by the students in regards of figuring out the last inch that they can run by chairs and do not bump into the walls?
Yeah, that's a very good question. There's actually a lot of stuff that goes wrong, and when you have the press there, they always wait for the robots to fail. Right? So whenever you are like in TV or so, whenever the robot fails, you can be sure that this is going to be shown. So yes, that's something, it's a lot. The most expensive one was a battery lost, like actually not being monitored anymore, and then draining all the chemicals onto the motherboard of the controller, which then, I think it was 130,000, this damage, right?
But still, this is something what we need to work on.
Yes.
and then there is a lot of satisfaction as well if you definitely reach the goal.
It's not only training robots, it's also training students. Right?
Yeah, and training them to give the right commands. Thank you so much, Wolfram. Really interesting. Keep on that good spirit and work. Great.